So I have it out, and then now it should be here. Right? So, but first of all, as I said, during March, I will motivate a little bit of a context regarding women in computer science. So today I wanted to show some important phases that have contributed to our science. And first of all, I want to refer to the Turing Award. I suppose that you know what the Turing Award is. It's the Nobel Prize in computer science. It is given by ACM, and it has been around since '66. And it was only until 2008 that Barbara Liskov was awarded with the Turing Award for her contributions on programming languages, and particular, well, data abstraction, etc., for tolerance, distributed computing, but particularly she was one of the people that initiate object-oriented studies too. So that was her, and then it was until 2012 that Shafi Goldwasser, together with Silvio Micali, obtained the Turing Award for complexity theory foundations on cryptography. Essentially, and then a lot of complex theory verification, these kind of aspects of computer science. And so for women that are involved in computer science, this doesn't mean that you did the bad choice because this is a boys club and there are no perspectives in the field. For women, this is not the case because, of course, the Turing Award is one of the most prestigious awards, but there are other ACM awards that are given to important works, and these phases show you from the very beginning of the science until very late in science that so these women are alive, they are proposing things, they're working, and they have brilliant careers and promising careers. And so if you are a woman, do not feel that the science is only a boys club, and if you are boys, do not be sad and think that you will remain just alone with other males in the boys club. We are here for you, and we will help you to to let computer science move forward. So this is for the little information about the context of our field. So yesterday what we started doing was really getting into the matter of the design of MapReduce algorithms. And we started with a very interesting problem that is kind of the type of problems that can be addressed parallelizing with this parallelizing model of MapReduce. Okay, so at the very end, we will see that there are some problems that are it is not possible to naturally be designed with the MapReduce model, but I'm going to present families and families of algorithms that it is possible to design under the MapReduce approach, and this is what we will be doing some of the sessions. So yesterday, the idea was a variation of the counting words problem, which is a seminal example of MapReduce. And the idea was, remember, if you remember well, was to given a log of posts, timestamped in the moment that they were posted, count the number of posts per user and give the first and the last time within an interval of time that this user posted a comment. And so this is very important that you bear in mind in order to design the solution. First of all, you have to think about the data structures. Like in any programming exercise, the data structures are very important to be defined. And since here we have a very generic data structure, key value, the design decision making is to determine what is the key and what is the value at the different steps of the map reduce setting. And so yesterday we concluded that in a first try to address the problem that the input of map can be designed as is given here. So we are going to consider that the key of the tuples, well, of course you have understood that what we represent is a list or a set of, it's a list of tuples, key value tuples. Okay, so this list, in this list, every tuple will be representing the ID of the user, and then the comment, so the string that represents a comment, and then the timestamp. And then the next data structure that we have to design, it would be the result that we are targeting after applying the map function. Without even, well, of course, we know what is the map function. The map function will process this initial set of tuples and will start preparing the right organization in order that we can count the comments and we can determine which is the first and the last time that a user posted a comment. So the result of the map that we are looking for would be a list of tuples where the ID of the tuple will continue to be the user ID, because we want, for every user, we want to know how many posts did she posted. So we will have as value a set of tuples like this. Now the fact that the person posted a comment and the time of the post. And this will be a list because we are assuming that every person can post several comments at different moments of the day. So we are looking, now if we think about functions or operations, we are looking for a function that will transform this data structure, well, the instances represented under this data structure, into instances that will have this data structure. And once we will have this, now we will have the user ID, the comments of the person, and the time. Now we can think about the final result that will be represented as follows. I would have the user ID, the number of comments that the person has posted, the mean time, and the max time. Okay, and here again, I'm looking for a function that will transform these tuples into this form, okay, by aggregating the values here. Do you have questions about this? Everything clear, crystal clear? Right, so if there are no questions, now what I asked you to do was to propose well, first of all, let's have a look at this, which will be how do we start from this type of input, and we produce an output that looks like this. So I'm going to stop sharing, and I will ask someone to share his or her screen in order that you can explain mechanically how would we would be the pseudocode to be to implement this transformation. So stop sharing screen. Right. So who says me? Please. I have to grant you presenter. I think that now I have granted you, Mauricio, I have granted you rights to present.
No, I still
No,
have.
not yet.
No.
How did I do?
No, I can see. I can share
Now you
now.
are?
Yes.
Yes. Okay. I think that I granted someone else also. Doesn't matter. Okay.
Well, I have it here. And
Mm-hmm.
well, first I started with the map function.
Mm-hmm.
Well, I started to first commenting like with natural
Mm-hmm.
language,
Mm-hmm. Mm-hmm.
the pseudocode. So first the function map receives a list of comments. For all comments, C belongs to list L, do, and I was very confused of how to
Wait a
read it.
minute. The list L, you have to, well, it's a pseudocode, but anyway, you have to provide the structure of the tuples of the list.
And how do I know? Does the exercise give me
Because
that?
you know, the preparation has been done before. What the map function receives is a list of key value tuples. Nothing else is accepted.
Okay.
Mhm. Yeah, that's something
Maybe
that I think that I didn't insist enough, is that there is some back-end cuisine for preparing the raw data into the structure that we propose. And
because they
so
are
then,
three
so
parameters,
L, you can
maybe
say
abstract.
L. There you are building them. What are you doing there? Yes, you
Well,
are building the tuples. In fact, this map is
yes.
for building for transforming the data, right? Is it?
Yes, I wanted to do the part where we have
Um,
the lists of
but
each
that's a
comment.
second problem. You see, we can do that. So we can imagine that we do under the MapReduce model the transformation of the raw data into the tuples that we define. Do you want to have a try on that?
Sorry, could you repeat it? I have my volume a
Yes,
little bit
in
low.
fact, the transformation of the raw data, so the strings, into the representation of the input on the key value tuples, a list of key value tuples, can be done also can be implemented using the MapReduce model. But this is a separate thing. This is this doesn't concern the problem that we are addressing. This is how do I transform strings into the key value tuples that I'm going to use as input.
Okay, yes, yes, that was the thing that I was trying to do.
Okay, so do you want, but that's not the right way of doing that. So that's why I am asking. Um, so you have to adjust some things.
Okay, okay.
Yeah. So, in fact, you are not, um, the comments are not just a string. The comments are already a structure. But the structure has three elements. It's a tuple of three elements: the ID, the comment, which is a string, and then the timestamp.
Okay. So I think it's okay to do it like this, no? Because it's like a struct, I can
No,
access it.
first the parameters. The parameters are not right because you have to model your parameter as a key value element. So you can, for example, do a record, a number of record, and then the whole data structure as a value. That could be some possibility. I think that I'm getting you lost, Ama.
Ah, yes. I,
So what
I'm
we
not
are
sure
going
what.
to do is we are going to do the transformation on the map reduce in a second try. Okay, we are going to simplify and we are going to assume that we are receiving. I'm going to write the tuple form in the chat, and so we can drop it. So your map will receive uh, list um, comment. I'm going to do post because it's short. Post and timestamp. So the input parameter of your map function must be, well, map, you open parentheses, you give the ID, which is user ID, for example, it's not to go, so user ID like this,
Okay,
and
yes,
the
I
value
forgot
is a
about the
tuple
tuple.
post timestamp.
Okay, yes, yes. Yes, I forgot that that structure of tuples. I was
Yeah, but that's it.
yeah,
Otherwise, I mean, we will see that in the lab. If you do not give that, you have an error. It doesn't accept
yes.
anything but key value. Okay. So so it's not a list. It's implicitly a list. Okay. So you have user ID.
So I do this
No, you can no
like this.
user ID as I said like that. Yeah. So ID and then value like this, post and timestamp. So you have the function map. You have uh, the key, which is the user ID, and the value is a tuple with two elements, post.
Mm. Okay.
Okay, everyone follows the idea. So we are abstracting, and that's what happens in MapReduce, the transformation of the raw data. This, we assume that someone else did it. So if we had an XML and we transform it to key value, if we have a graph and we transform it into key value, that operation, we assume that it's done, okay? And that we, as input, have a structure where we specify in the map the user, well, the key and the value, where the user can be a data structure and the value can be a data structure or an atomic type. So in our case, the key is an atomic type, which is an integer, and the value is a structure, which is a tuple of two elements. One with two attributes. One is named post of type string, and the other is timestamp of type date. So if you really want to be precise, what you would do is user ID for a type language. Like this. And please
Okay.
note that the value is a data structure, but it's one batch of data. It's the tuple that integrates both elements into one thing that it's a value, but it's a data, it's a structure. It's not an atomic type. It's a complex type, right?
Yes. Well, and for example, so where do we store this? It's just that, for example, we're in a tuple, right? In a structure tuple,
Yes, the
or
tuple is here. The tuple is post. It's well, these brackets represent a tuple. A tuple is a series of attribute value elements, no? And this tuple has two elements, one of type string and the other of type date. But it's one data structure,
okay.
right? Everyone sees that. Do not get lost. Ask. This is important. Okay. So now we have these, and now it looks, I mean, your pseudocode looks more or less this right, because what we want to do, I'm going to write here the target again in the chat, the target data structure. So as output, we want this. So we have to iterate and on the list of this input data structure, and we have to build a new data structure where we have as key always the user ID, but then as value the fact that someone posted a comment and the time. So imagine that I get this. So I have this, and I want to transform this tuple into a new tuple where I have the user ID and I have a one, since I have here a post, I have a one here and the timestamp, and the timestamp as value. So what do I do in my pseudocode? So for every
user ID.
tuple in the list,
For every tuple.
for every
So
yes, you can say for every post. Let's put it like this: for every, not for all, for every C, every C in L. Well, let's say that the initial, well, the list is called L. Okay, in L, and then what do we do? We
I put this right
what? You put
at the
that.
tuple or
Yes,
not.
but note that it's more complex than that, because I have to bear in mind I'm looking for all the, I'm doing a group by, I'm looking for all the comments of user one, all the comments of user two, you see? So I have to get the first comment, initialize, in fact, I have to initialize a list for every user. And so for every user, I'm going to say, I get the first tuple. I see whether I already have a tuple concerning the user. If I do, I'm going to add an element to that to the list of the comments of the user. And if I don't, I create a new one for the next user. So stop sharing, and I'm going to explain it with
Okay.
words, and then we come back to your. So. So essentially what we have to do is I get the first one and I say, I have user one and I have a first comment. So I have one and I have the timestamp and I close. And then comes a new tuple, and does it concern user one or users that I have already visited? No, it's a new user. So I create a new data structure with ID, the number of the user, in this case is 2, and then the fact that she did a comment at 8:35, and I leave it there. Then I go to the next comment, and I see the user ID. Is the user ID already in my list? Yes, it is already in my list. So I'm just going to add to the list of associated comments the fact that she posted a new comment at 9:24, and I stop. Then I go again and I see this new comment and I say, this concerns user one. Is user one already in the list? Yes, there is one in my list. So I'm just going to add the fact that she commented again at 9:32. Then I come back and now I have a comment by user number two. Does user number two exist in my list? Yes, she is already there. So I'm just going to add the fact that she commented again at 8:52. Then I come and I say, I have a comment from user three. Is user three already in my list? No, she's not. So I create a new tuple with the number of the user and the fact that she commented at 10. And I'm done because I do not have more comments. Does this make sense?
Yes, so we first like iterate to for each user, right? So we find the user one, and then we add all his tuples.
Yes.
Well, something like that, until we arrive to the last user.
Until end of file.
Okay.
Right? So that's first thing. So of course, we know computing for a long time ago, we know that what we're doing is a group by. We're just implementing group by, right? So if in a pseudocode, if you do not want to explicitly say all the implementation of group by, you could say group by user, and then you do comment and time. So one and time, and then you, I mean, it's done. For a pseudocode, of course, if there is no, if you have really to implement that, you have to implement group by, because here we are using just a programming language in order to do that, and it depends on the programming language whether we really have libraries that implement group by or not. So I don't know, Go, Scala, F# or whatever, Python, but that would be another problem. So is this clear?
Yes, well, yes, yes, I believe.
Right? So the others, are you sleeping? Is it Sunday? Alexander, please.
Thank you. I just have one question, and it's that, for instance, from the original list of tuples to the following data structure at the top right, the curly
This one?
brace, yes, is that structure
It's a
exactly.
list.
Those curly
It's
braces.
representing well, it's a list, it's a set, but well, I'm referring to a list because we can, it's a set because we do not longer have duplicates.
All right, so it is a set. Okay.
It's
Okay.
a set of items that have this form. One here, just that so that you do not get lost. This is an integer, and this is a date. This is a string, and this is a date, and this is a string, integer, and this is an integer. Okay.
Okay, I see.
You see, and so, well, here I was not very rigorous because I didn't say that it was a tuple, so I could have said like tuple, and here again tuple. So this means that I have a set of tuples of the form integer date. And here we have an instance of it. I have my set, and every tuple has an integer and has a date value. Is it clear now?
Yes, this also assumes that one user can only do one comment per minute, no? Because
Well, there is no parallel Twitter, for example. And of course, if you are considering time, you have forcefully a point in time, only one point in time per comment, since we are just observing one source. If we were, even if we are not observing one source, I mean, we suppose that we are not bots, that this is people commenting. Otherwise, we would have problems on that. Well, no, here we wouldn't, because we would say that 1 and then 8 but then we are not dealing with a set, we're dealing with a list. So instead, if I was considering what you're asking, so let's consider that I can have two comments of the same user at the same timestamp. So instead of this, I would say this.
All clear.
Okay.
Thank you, Doctor.
You're welcome. Other questions? It's a little bit arid, I know. It's just a little shot of this and then we go further. And then the second, I'm going to let you figure out at home for the pseudocode, but then the second, it's just the same idea, but in order to aggregate. So we have these tuples, and now I want to transform them into this form. So what would I do? I would get the first tuple and I say, the user ID is the user ID. I'm going to aggregate the number of tuples, 1 plus 1 plus 1 is 3. And then I will compute the mean of the time and the max of the time, and I will build my tuple. So, and then I go to the next tuple and I have user number 2, 1 plus 1, she has posted 2 posts. The earliest moment at which she posted was the minimum between these two is 8:35, and the maximum of these two elements is 8:52. And then I go to the next one. I only have one element, so 1 is 1, and then the mean and the max are the same. And so you have to write an algorithm, I mean a pseudocode that processes every tuple by computing the summation of the elements of the tuple, and then the mean and the max of the dates contained in the different elements of the list or the set according to the hypothesis that we make. Right? Clear? Are you having a heart attack?
A little bit. No, no, it's just that the problem I had doing this was finding the data structure. I was first thinking about a dictionary or a hash map, but it was a little bit complicated.
No, because here you only have key value. It's like relational. In relational, you only can have relations, tables. Here, you can only have key and value. And anything you have, a graph, whatever, you must use key value to represent this.
Okay.
And you are right. The hardest part of this is defining the right data structures. Because once you have the right data structures, then you can see more or less how to transform, and then you can more or less easily do the pseudocode. But the right data structure is of course a problem. And of course, there are many different possibilities at some point, and then you have to decide to see which is the best.
Yes, because the dictionary, the limit I had is that the key has to be unique. So it's a little bit like difficult to manipulate it.
But the dictionary is not a valid data structure here.
Why not? It is that you
because
can
in
put
a dictionary you can have, it's like a kind of it's a record, no? if you're talking about Python. So you have
C sharp.
and here you can only have one key, and that can be a data structure, and a value that can be a data structure itself,
Mhm.
but nothing
Okay.
else, no dictionary.
Yeah, okay, yes, because if I put a dictionary, it will be another key if I want to. Yeah,
Yes, yes.
yes, you're right.
See? Mhm.
Yes, that was also
And
my
it
problem.
is very restrictive, and this is why it's complicated.
Yes, I had.
Because suddenly it's like if we have a language with only one data structure. Right? Imagine that we want to speak and we have only two words that can be used: stone and water. And we have to say everything with stone and water. It's like that. You must represent anything with key and value
Okay.
and nothing else, right?
Okay.
So it's like how to compress the different elements of your data such that they fit into key and value. That's that. And of course, you have identified the challenge. The challenge is the data structure. Other
Okay.
comments or questions? So again, you can sit down under the sun at some moment, have a coffee, and then you complete with pseudocode so that you have the complete picture of them. Because now here of course I focused on the data structures because this is the hardest part. I didn't, and I will not go through the pseudocode because I mean it's more or less easy to define, but I think that you should try to do the whole experience out of what we have discussed now so that you have the complete picture of the design of the solution. Okay, so eventually you can also have a look at my slides, and then well, I provided at least for the reduced part some a try. And then what you have to consider is that going from here to here corresponds to your map function, and then going from here to your reduce function. And there are many different problems that we can, of course, that we can identify to be solved under the MapReduce setting model. Just give me a second. I make sure that I'm using the right thing. Yes. Sorry. So we will see later on that in fact we are now not going to start from zero, because as the gamma patterns of software engineering, here you have the gamma, well, not gamma because they were not proposed by gamma, but the patterns, MapReduce patterns that help you figure out how to organize your data, and then what you can implement in the map and in the reduce function in order not only to have a solution, but eventually to have a performance solution. Okay, so if it becomes hard, you have these patterns and you can refer to them, and this can help in order to address the problem. So again, for home, you can consider, for example, well, here what we did is we did the maximum and the minimum. Okay, so an important thing that it was the fault of Mauricio that we didn't see, but that you can have a try again at home in order to have the big picture, is how do you transform from the initial data into this key value input format. And this can be done also under a MapReduce setting. So a very nice exercise in order to complete the problem here would be to propose a MapReduce setting in order to transform your initial data structures into the input. And again, you will find the same strategy. You have to define your data structures for the initial input of your map, your reduce, and then the pseudo algorithm. So that's something that you can do in order to be sure that at least the principle, you get the principle, and that you can provide a solution on this. Now, there is something that nobody asks, but that I'm going to put into the table is well, when I introduced the counting words example, I said that there was a map, a reduce, and something in between. And here in my example, I didn't have anything in between. Okay, so question is there something that I can consider in between that in order to transform the output of map into the input demanded by reduce? If this is the case, I need to have this shuffle sort part. So, and this is another, well, this is the second level, okay? We can first think without this, a solution, but then once we have the solution, we can have a look and see whether we can do something in the intermediate result of the map in order to prepare the data for starting the reduce. In my example, I think, for example, to be done would be that that instead of providing this as this, I could, for example, already in the map do a count of these elements. For example, I could have computed the size of my set. If I compute the size of my set, I know the number of comments, and I already provide a pre-defined, pre-prepared input into reduce in order to reduce the amount of work to be done here. Another thing would be if I allow, as we suggested, if I allow duplications, something that I could do is here, if I could have duplications here, would be to group duplications together, okay, in order to pre-process the output of the map, and then have less burden in reduce. Or I could even compute the summation, the max, and the mean, and then only build the final result in the reduce and delegate everything to the map. I perform almost everything into the map. It goes smooth, I mean, directly to reduce, and reduce only builds the final results. So these are many possibilities that I can imagine in order to have a setting where I have something in map, I have something in the middle, and I have something in reduce. And what will guide my decision? The number of resources that I'm going to use to implement it. Okay. So now in real world, what happens is that you run a lot of settings and you see. and then you choose the one that is most performant. That's the way it's done today. So what it is important to do is to redefine, in fact, the specification of map and reduce. In fact, what you will have in order to implement a map reduce solution is, well, here I exhibited the initialization. You have an initialization process in which you are going to transform and prepare your initial data collection, and you are going to fragment it. Okay? So that's something that it's done behind the scenes. Once you have done this, and fragmenting it means putting the right data in the cluster nodes that will then host the map functions and then the map functions. And in fact, what map does is it has a record reader, it has a mapper, a process. So map is implemented in several processes. One is a record reader that will go through the input. It will have a mapper, that is the process that implements the map function. It will have a combiner that groups and prepares, organizes the output, and it will have a partitioner that will distribute the results into a number of reducers that will then produce the result, the final result. Okay? So this is, I mean, of course we see map, but behind the scenes we have several processes that run in order to perform our solution. And then the reduce function is implemented again in several into several processes. One is shuffle and sort, which is the intermediate transformation of the map results into the input of the reduce function. The process that actually implements runs the reduce function is the reducer, and then the one that stores the results into the shared space is the output format process. Okay? So these are the processes, and then here and here, before, in order to prepare the inputs, what will happen, particularly in the initialization phase, is we are going to partition, so as I said, to fragment the key value pairs into chunks. Now you are familiar with partition and with chunk. And then the maps, several processes will run the map function applied to one of the chunks partitioned at the initialization phase. Then once all the maps are terminated, every process consolidates the values and produces an emit key. Okay, the result that you produce out of the map function is an emit key, and then it's represented by an emit key, and then you will partition again the output of the map according to the keys, and then you will run the reduce function in parallel again, and then you get the result. So this is to exhibit all the phases that are implemented when running our map reduce setting. Because when we're here we never see the parallelization. We're just seeing a sequence, a pipeline of activities. There is initialization, then there is map, then there is shuffle and sort, and there is reduce. But here we are not saying any parallelization at all. The parallelization is done behind the scenes at runtime, and the parallelization consists in dividing the initial data into chunks, putting them into different nodes of a cluster, and then sending to every node of the cluster that is participating in the execution the map and our program. You can see our program as a map reduced composition. So it sends the program to every node, and then the node executes this program, which means executing the map and the reduce function. Right? More or less clear? Questions? It's a little bit hard.
I have a question, teacher.
Yes.
Well, just I think I don't understand it. So we do the partition. So we have different
No, we
chunks.
do not do the parallelization.
No.
The parallelization is done by an infrastructure.
Oh, okay. Yeah.
This is what I meant when I showed you this. Here, there is no parallelization. We're just defining a pipeline of 4 steps: initialization, map, shuffle and sort, and reduce. This is not parallel at all.
Yes. No.
Right? So the parallelization will come at execution time, but not at design time.
Oh, good. I understand.
You see? And this is why many people that do real parallel programming say, well, this is not parallelizing. This is just define. I mean, it's a transparent way in defining functions, and then you delegate everything to the infrastructure. Okay, but it's quite clever because this implies that even us that have not have a course on parallel programming, we can still do parallel programming thanks to all this infrastructure that is there in order to execute these processes in parallel, but in a transparent manner. And this is why my disclaimer at the beginning when we started studying MapReduce was that I'm not teaching parallel programming, okay? I'm just teaching a way to design functions on data for processing data that will be executed in parallel. That's all
Oh, okay.
what I'm doing, right?
Yeah. Thank you, teacher.
Yes, I mean, for the records, if we would be programming in parallel, the first thing that we would do is understand the architecture. So as we have, for example, RAM in a classic architecture, there is PRAM. And so we would have to understand the characteristics of the architecture in order to be sure that we deploy our processes in the right way. How to communicate and how to exchange data and how to consider all this in our program such that it runs in parallel. So it's another paradigm, programming paradigm that I'm not touching. Okay. This is what you would have to do if you were learning parallel programming. So what I have said now, it's given here, okay? It's just that eventually when I upload the slides and you see just a figure with 3 elements, you can know what it means. And here in this slide, this is written what I have said orally in the previous meetings. Okay? So for every subphase, what happens, etc. And this is, so you have it for the map subphases. So the explanation that I gave here is given here, and the explanation that I gave for reduce is given here in the reduce subphases. Okay, so if you didn't have time to make notes about it, do not worry because it's there, and It's, I mean, well specified so that it, hopefully it's clear. Now, at the very beginning of when I started introducing this MapReduce story, I gave an example of pseudocode where I showed that, for example, in considering that we would be in an object-oriented programming setting, for example, Java, what you have is classes, already libraries that provide the class mapper and the class reducer, which is the name of the process that is going to execute the function. And then every class mapper has a method map where we specify our function. And then for reducer, we have a function reduce, and the algorithm. And if you have a look here, these lines emit, build the output data structure in terms of key and value, as we have defined before. Before I go to the local aggregation, etc., I wanted to show something else. Just give me a minute. I don't know why. Yes, here. So how does it look? Okay, we have our class map and our class reduce. We know how it has been designed because now we master counting words. And now, how does it look like in at runtime? So at runtime, what will happen is that here you have the initialization step that I previously described. So the initialization step will fragment the collection and will provide every fragment to a process mapper. The process mapper will perform our function and it will produce the results according as we specified in the function. Then we use shuffle and sort, which means aggregating values, etc. is not implemented by us. Okay, it is implemented by the infrastructure. The data is thus prepared. For example, here it has aggregated values. You see here we have A is 1, B is 2, etc. And here we have all the outputs that concern A in one, aggregated together. Then for B, we have everything that concerns B aggregated together, and then C aggregated together. So this is the input for reduce, and then it is again fragmented and given as input to the processes reducer that will execute the function reduce. And now the reducers provide the final result, okay, which is given to the infrastructure. And who says how many mappers and how many reducers? Who decides that? The programmer. The number of mapper and the number of reducers that you are going to have in an execution is predefined when you configure your architecture. So there is a tuning process that has to be considered by the administrator of the architecture of the environment in order to say how many mappers can you run for a given program, how many reducers can you run for the same program, and how much main memory and execution resources you will allocate for every process. And in order to, since you are looking for performance and execution time, you will play with the configuration of the environment and with the number of mapper and the number of reducers in order to find a setting that runs best your solution. And this is what becomes complicated. And this is where we are, us as computing engineers. This is our job. Okay, have tests and see how is best, how are resources best allocated such that a given process can run in a performant manner. Questions here? No questions? Yes?
Well, I had a question on, say, if this example is to count the number of occurrences of every word in a text collection, why does the reducer, I was thinking that the reducer would sum, say, for example, A, if the key A has values 1 and 5, I would have thought that it would reduce him to produce a 6.
Yes, here it's not the right number of occurrences.
Okay.
It's taking the maximum.
Yeah, yeah. Okay. No, that was my question then.
Yeah.
Thank you.
Something else? This means that you are paying attention, so thank you for that.
You're welcome. Thank you.
So there was someone else with a question. No? Okay. So I'm going back into my slides. And so I'm going to give, no, it's almost time. I'm happy with the MapReduce stories, and you kindly do not tell me that it's time and I didn't put my alarm. So, okay, so what we will do next, I wanted to give a little bit of homework for the algorithmic part, but we are not, I'm not going to do that because you have your second rounds, etc. So what will happen is that in the lab next time we are going to run some examples on top of Hadoop. So I'm going to explain what Hadoop is, etc. How does it work, and we will run some examples in order to that you see how does it look like to run this and what are the implications of that in code and running time. And so we will go back and forth having this type of executions in the lab, and then some algorithmical aspects. I will try to be more dynamic next time so that we figure out and understand the very general principles of the main families of algorithms that can be designed with MapReduce. And with that, we will close the Hadoop aspect. Then we will see another alternative with Spark that will be much more dynamic. And with that, we will have seen the principles of data processing at scale. Okay, so we went from storage. Now we are we went through analytics. We are seeing how processing is done at scale. And at the very end, we will see how to configure virtual machines, etc., so that all this can run in different architectures. Okay, so that's the big picture. But for the time being, I'm going to liberate you, and I'll see you on Tuesday if you do not have questions. Have a nice weekend. Do not hesitate to ask if you still have questions for Monday's second round for the lab. Nice weekend for everyone. Bye-bye.
For now, I think everything okay. Thank you, doctor.
Excellent. Bye.
Enjoy your weekend. Have a nice weekend.
Yes.